Greetings, fellow students. We are continuing with our lesson today. We are on lesson 5 of Engineering Science and 3. My name is Mr. C. Tomejani from Ehlanzeni TVET College. And today we are continuing from the previous lesson of heat. If you can remember very well, we were looking more details in the heating of either steel or water. So we're speaking in particular about the specific heat capacity of a substance, and we're also speaking on the transfer of heat energy. Now today, we are not going to be dwelling much on what we did last on the previous lessons, but today I want us to look at more particularly the other aspects of heat. The likes of the calorific value. We are going to look deep into the calorific value, the coefficient of linear expansion, as well as the area expansion, or rather the superficial expansion. Now, what is the calorific value? Like we said before, calorific value is the quantity of heat released per unit quantity of fuel, or rather to burn fuel completely. The amount of heat required to completely burn fuel, or the quantity of heat required to completely burn fuel. Fuel, we have two types of fuels. We have liquid fuels, which can be petrol, paraffin, anything that is liquid and it's flammable, that is a liquid fuel. And we also have solid fuels, which mostly we use coal as solid fuels. Coefficient of linear expansion, they say here, is the increase in length per unit length of a material per degree rise in temperature. If you have an object that has a certain length and it undergoes a certain heat, this object will increase in length. So we are looking at the coefficient of linear expansion. That is the amount of heat which might be required to change the length of that object. And then the superficial expansion, this is the amount of heat which is required to change the area of an object, or the amount by which a unit area of a material increases when the temperature is raised by a degree. Here's an example here. They say water at the temperature of 18 degrees Celsius passes through a gas-fired boiler at the rate of 250 liters per hour, where it is heated to a temperature of what? Of 90 degrees Celsius. The gas used in the boiler has a calorific value of 18 megajoules per meter cubed. And the water has a specific heat capacity of 4.2 kilojoules per kg degrees Celsius. If the efficiency of the boiler is given as 80%, we need to determine the following. Now let's try to unpack what is happening there. Now let us extract our data from this statement which is given to us on the screen there. They say water has a temperature, or rather water at the temperature of 18 degrees Celsius passes through a gas-fired boiler. So, extracting our data here, what do we have? We have the mass of water, which is 250 kg per watt per hour. In an hour, we have 250 kg of water passing through a gas-fired boiler. Now, the initial temperature of water is given as 18 degrees Celsius. Now, they say here the water, when it passes through that gas-fired pipe, or rather boiler, the water then increases its temperature to 90 degrees Celsius. T2, 90 degrees Celsius. And then they say the gas used in the boiler has a calorific value. So now we're speaking of the gas. So we're going to have a separate data for the gas. The calorific value of gas, 18 megajoules per meter cube. And the water has a specific heat capacity. The water has a specific capacity of 4,200 joules per kg degrees Celsius. You can choose to use 4.2 kilojoules per kg degrees Celsius. It's up to you how you want to go about working this thing. But at the end of the day, you must ensure that the same value that you obtain with its SI units must be reflected. Now they say if the efficiency of the boiler now
efficiency of the boiler is 80%. When we speak about the efficiency of the boiler, what are we referring to? It means that in the process of transferring heat from the boiler to the water, heat was lost in between. Or rather, heat was spread to the surrounding of the boiler, since the law of energy says heat cannot be lost. Now look at this. Water passes through that boiler. This boiler has a gas at the calorific value of 18 megajoules per meter cubed, right? So it means that the boiler already is producing heat. The gas is giving the boiler 100% of the heat, right? But the boiler, it's giving the water only 80% of the heat. Now, they say, determine the energy absorbed by the water per hour. Energy absorbed by the water per hour. Let me do that. The energy absorbed by the water per hour, Q of water, we know that it's given by MC, change in what? Change in T. What is the mass of water per hour? 250. 250. The specific capacity is 4,200. 4,200. And the change in temperature, T2 minus T1, that is 90. Minus what? Minus 18. Let us punch that in our calculator and see. 250 multiplied by 4,290 minus 18. We get that value. Since it's a large value, we're going to divide that by 1 million. Let's divide that by 1 million. Let's divide that value by 1 million. This value, dividing it by 1 million. If we divide that by 1 million, it means we're going to have 75.6 megajoules. Why am I dividing this value and not putting it as it is? There are some cases where the number should be easily readable. If I'm having 75,600,000 written on the board, that is like a very large number and sometimes stressful to read. So if I just divide the value and make it user-friendly or reader-friendly, then it becomes simple for other people or even for the marker during an exam to easily understand what is it that you're trying to portray with that. Now the next question says the useful heat supplied by the gas. Now this is a very tricky question. Let me try and unpack it for you. If the gas produces 100% of heat and only 80% is absorbed, right, by the water. And then now the first question says calculate that heat which is absorbed by the water. And we found that the heat which is absorbed by the water is what? 75.6 what? Megajoules. Then what is the useful heat? Correct. This means that the useful heat will be equal to the absorbed what? The absorbed heat, which is 75.6 megajoules. I don't have to calculate that because I know that is the energy which I obtained in the water. Then obviously that is the energy absorbed by the water. And then the next says calculate the calorific input of the gas per hour. Calorific input. Now, remember, the water takes only 80%, right? While there's 100% being produced. We want to know what is that 100% that was produced or that was transferred to the boiler. We know that the boiler produces what? 80%, which is 75.6 megajoules. We want to know how much was transferred to the what? To the boiler. How are we going to do that? We use the efficiency equation. Efficiency is given by what? Output, input, multiplied by what? 100%. What are we looking for? The input. We are looking for the input. My space here, let me write it here. We're looking for the input. Mathematically, if you derive that, you're going to have input is equal to output divided by efficiency multiplied by 100 what? 100%. What is our output? 75.6. Efficiency, 80 multiplied by 100%. What do we have there? What is it that we have? If I'm having 75.6 divided by 80 multiplied by 100%, the calorific input of the gas to the boiler is 94.5. 94.5 megajoules. The calorific input will be 94.5 megajoules. The last question here says now the gas consumption per hour. Now look at this. We know that 250 liters of water is supplied to the boiler per hour, but we don't know how much gas is supplied per hour. So we need to find how much is supplied per hour. We know the amount of energy which is supplied, but how much is supplied? And then we go to our equation Q. Q is equal to VCV. Because this is liquid, then V will be equal to Q over CV, which is what? 94.5 divided by 18 megajoules. This is 94.5 megajoules divided by 18 megajoules. This should give us what? This should give us 5.25. 5.25 meter cubed. 5.25 meter cubed. That is how simple it is. You only need to understand your equation, understand what you're dealing with, which formula you need to use, how to use that formula, when to use that formula, and why to use that particular formula. Understanding those simple concepts will make everything simpler for you. Now, that is the part where you deal with the calorific value of fuel. But what about the part where you deal with the coefficient of linear expansion? Now let us move to the coefficient of linear expansion. We said coefficient of linear expansion, what is it? This is the amount of heat required to change the length of a substance. Now, if you apply heat to an iron rod, right? You apply heat to an iron rod, the iron rod has its original length. When you apply heat to that iron rod, what happens? The iron rod will change in length, depending on the amount of heat that you're applying in that particular iron rod. Equation is projected there, where the change in length is given by the coefficient of linear expansion, which is what? Alpha, multiplied by the original length of that particular iron rod, or just the rod, multiplied by the change in temperature. That is the equation there, where the pi L, that is the change in temperature, delta L, change in temperature, what? Change in length, I mean to say, that alpha, that is the coefficient of linear expansion, LO, that is the original length, and so forth. Understand how to apply these formulas, more particularly when it comes to examples. We have another example here. They say a steam pipe has a length of 2.5 meters at 15 degrees Celsius. What does this mean? We have a steam pipe that has a length of 2.5 meters at a temperature of what? 15 degrees Celsius. Now, steam, which has a temperature of 235 degrees Celsius, is passed through the steam pipe for several hours. If the coefficient of linear expansion of the material from which the pipe was made is 12 exponent negative 6 per degree Celsius, calculate the increase in length that the pipe will experience. Right. Let us take out our data. What are we having? We have the original length, LO, which is 2.5 meters. We have our initial temperature, which is 15 degrees Celsius, right? And then we have steam, which is passed through this pipe. When this steam is passed through this pipe for several hours, and the steam has a temperature of 235 degrees Celsius, what happens to the temperature of the pipe? It changes, right? It changes to a point where the pipe and the steam has an equal temperature. This means that T2 will be 235 degrees Celsius. Right, and the coefficient of linear expansion is given as 12 exponent negative 6 per degrees Celsius. Now, the first thing they want us to do here is to find the increase in length that the pipe will experience. How do we do that? We apply that equation that we had. Change in length is equal to coefficient original length multiplied by change in T. What is our coefficient? 12 exponent negative 6. Original length 2.4. Change in temperature 235 minus 15. 235 minus what? 15. Now let us find what that is. 12 exponent negative 6 multiplied by 2. Is it 2.4? No, it's 2.5. 2.5. 235 minus 15. This is what we have. We have 6.6 milliliters. But in most cases, when we work on this one, we need to work with meters. How do you go about converting that to meters? You multiply it, or rather you divide it by 1,000. If you divide it by 1,000, you're going to have 0.0066 meters. This is the change in length. That is the change in length. And then the next question, they want us to calculate the final length, right? The final length. This is the increase in length. Now we're looking for the final length. If the length increased, right, what will be the final length be? This means that the final length will be the original length plus the change in length, because this thing has increased in length. 2.5 plus 0.0066. What is the final length? 2.5066 meters. Simple. These are the most critical questions that you need to understand before you attempt any questions. Know what is it that you are given, know when to use it and why to use it, more particularly when it comes to these kinds of questions. So you need to learn to treat more question papers. You see, when you treat question papers, make time, have a day that today I'm treating only question 1 of these question papers. Tomorrow is only question 2 of so much question papers and so forth. Don't treat the whole question paper in one day. You'll end up confusing yourself. Now let us move to the superficial area. Superficial area. Superficial area. The equation for a superficial area is given by area is equal to the original area into 1 plus beta change in T, where this area, which should be the change in area, is equal to superficial area. AO, that is the original area. Beta, this is the coefficient of area expansion. Coefficient of area expansion, in most cases, they don't give you. You are not given the coefficient of area expansion. They would only give you the coefficient of linear expansion. So to find the coefficient of area expansion, you need to multiply the coefficient of linear expansion by 2. Then that is the area expansion. And then the change in temperature. Let me just rewrite the equation. It should be given as AO 1 plus beta change in T, right? Or it can be the superficial area is equal to the original area into 1 plus 2 alpha change in T. What is 2 alpha? We know that alpha, this is the coefficient. This is the coefficient of what? Of linear expansion. This is the coefficient of linear expansion. So if you multiply it by 2, this will give you what? Beta, which is the coefficient of area expansion. But now, it is very much important to know how to go about applying that. How to go about applying that. How do we apply that? We'll see it on this question. Now, we have a square brass plate which has sides 400 millimeters at 12 degrees Celsius. What will the increase in superficial area be if the temperature of the plate is raised to 100 degrees Celsius. And then they said the coefficient of linear expansion of the brass is 0.00002 per degree Celsius. Let us extract our data. We have a square brass. If we have a square brass, that means the area will be equal to the 400 millimeters. It should be 400 millimeters multiplied by 400 millimeters. Because we know that a square has all its sides are equal, right? So the equation to calculate the area of a square, it can be side by side or side squared. It's up to you how you want to go about calculating that, but it's important to know how you go about calculating that. But first, let us find the meters of these values. I believe this will be 0.4 meters, 0.4 meters. It should be 0.4 meters, right? 0.4 meters. This gives us what? 0.4 times 0.4. This should give us an original area of 0.16 meters square. They say this is at a temperature T1 of 12 degrees Celsius. Now, what will be the increase in superficial area? The increase in superficial area, right? The increase in superficial area if the temperature is raised to, what? To 100 degrees Celsius, and then the coefficient of linear expansion. Coefficient of linear expansion is 0.00002 per degree Celsius, right? Let us calculate that now. What is the superficial area? Equation to calculate superficial area is given by A is equal to AO into 1 plus beta change in T. What is beta? Beta will be equal to 2 times alpha, which is 2 times 0.0000002. What will the answer be? There, we have 2 times 0.00002. This will be 0.00004 per degree Celsius. And then now we can jot in our information there. Change in that will be equal to AO 1 plus beta change in T. The original area, it's given here, that is 0.16 into 1. Let's put a square bracket here. Let's put a square bracket 1 plus 0.00004 into here 100 minus what? 12 degree Celsius. Let us punch that. Let us put that in our calculators. This should be 1 plus into 0.00004 into 100 minus 12, like that. And then this would give you what? 0.161. 0.161 meter squared. What is the change? What is the change exactly? Now, we find the exact change of the area. The exact change of the area should be the original area minus the superficial area. Let me put it that way. The superficial area. Let me also fix here and put it as like that. So it will be 0.16 minus, it should be the superficial area, I mean to say the superficial area minus the change in area. So this will be 0.16, then the change will be 0.001 meters squared. That is basically how you go about doing it, and that should bring us to the end of our lesson today. Let's hope everything was easy. It was understandable. If you have any questions, you know where to reach us. Our website, ehlanzenicollege.co.za, YouTube, Ehlanzeni TVET College, on Facebook, Ehlanzeni TVET College, on Twitter is @Ehlanzeni TVET. And you can ask any questions there. You get your correct answers, you'll be assisted. And the best thing to do is to always study and stay safe. This is it for me today. Until maybe we meet next time. Cheers.